Hello, this is Tim Malloy with video 1-2 on Gauss's Law. I'll be doing a problem with a charged sphere. So a solid sphere of radius 40 centimeters has a total positive charge of 32.1 nanocoulombs, uniformly distributed throughout its volume. Calculate the magnitude of the electric field at the following distances. Distance 1, 2, 3, 4. So we've got our work cut out for us. So right off the bat, electric field, sphere, those should be your red flags to understand that we're going to be using a Gaussian sphere to understand the electric field, and that this sphere, I'm sorry about that, and that the sphere is an insulator. Okay, so let's find the formula for a Gaussian sphere on our own. You should probably know this, but during the exam, they might ask you to not to find it on your own, and you're gonna know how to, and you're gonna have to know how to do that. The answer be damned. So first off, we start with Gauss's law, and so we have electric field times area of your object. So that would be our sphere. Oh, and I'm sorry, I should probably go over this. So this is our sphere that they're talking about, radius A of 40 centimeters, and then we're going to be testing it at different radiuses. I'm sorry. So electric field times area equals charge enclosed over epsilon naught. And we know the ratio of Q enclosed over volume enclosed is equal to total charge over total volume of the object. Set this equal to Q enclosed, and then put it into Gauss's law on the right side. Do some simplification. Do even more simplification. And then for 4 pi epsilon naught, we know that 1 over 4 pi epsilon naught is equal to Ke, our constant, our Coulomb's law constant. Sorry, I just wanted to give the name of that because there are a lot of constants. It's probably important that I know how to tell them apart. And then for that, we can reach our formula for a Gaussian sphere. Okay, so part A asks to find the field at 0 meters. So if R equals 0, then so does electric field, because we're multiplying this entire thing by 0. So simply put, electric field equals 0 nanocoulombs. Newtons per coulomb, not nanocoulombs, sorry. Part B asks us to find it at, I believe that's 10 centimeters. I'll double check. Yes, 10 centimeters. And our R is our changing radius, remember. That's the test radius, I suppose, and this is the radius of the entire sphere. So we plug in our 0.1, plug in our 0.43, plug in Ke's value, plug in the charge's value, making sure to convert to regular coulombs, and then we get this big number, which we simplify to 451 kilonewtons per coulomb. And I believe the electric field points inwards, because you have, we know that electric fields flow from positive to negative. So these would all be, and test charges, whatever, are positive. So that these would all be pushing all these charges that are on the outside, or not the outside, but the edges of an insulating sphere, which is how they work. They all point inwards. They all point away, and that's why I suppose your electric field in the center is also 0, because it's canceled by all of these. I hope that made sense. Because I have trouble understanding this myself, and it's really only starting to click the more I do it. But it's probably important. So at part C asks us at 40 centimeters, which we know is the same radius as the object. So in that case, we canceled a radius, so that's why we only have 0.4 0.4 meters squared, not 0.4 meters cubed. I just canceled. Then we get 1805 kilonewtons per coulomb, and this is on the edge of our spheres, and I believe it is pointing outwards. That makes sense. It's like really, yeah, I believe, yeah, this is where the electric field is the constant. I will get into more of that later when we graph our findings. And so D says to find it at a point, I believe 6.9 centimeters, which is outside of the sphere's radius. Okay, so now we're past slash outside the sphere. Volume is not increasing, and nor is charge. We can use the point charge formula, and here's our physics explanation. Again, starting with Gauss's law, plug in for area, and again, charge isn't changing because because with part B, it was we only had part of the sphere, and then with part C, we had all of the sphere, and now with D, we have also all of the sphere, but no more charge because it was all in the sphere. So plug in area, again, charge is constant, whatever. And then simplification to the point charge formula that we know from last year. Plug in our values, making sure to use our testing radius, I suppose, or distance from center, which is 0.69 meters squared, 607 kilonewtons per coulomb, and points outwards again. And let's graph the data. So remember, A is at 0 at the center, where there is no electric field. And as we go closer towards the edges of the sphere, the electric field increases. Remember, we tested that at B. And then at point C, sorry, I just like showing this because I think it's a good way to understand. Point C is the greatest. And then it only gets worse from there, weaker from there, only getting further from the, field generating charges. If you get away from the charges, the field decreases. We know that very well. And I have all the answers checked over here, just in case, just to establish my credibility. Okay, so the takeaways that I have are to know that when we use Gaussian spheres and shells, it gets a little more complicated. So I suppose this is your warm-up. And it's important to know the properties of conducting and insulating spheres, how in spherical conductors you have no electric field inside, and you have no electric field inside, and the charges spread out to the edge, where in the insulating sphere, the electric field exists inside, and there's charge all around. Okay, so I think that should cover everything. Thank you for watching.